So, what do I want to talk today? Is about, as I have written in my title of my talk, is that it's a small step towards computing arbitrary M2N scattering amplitude at large N at exactly up to all orders in tube coupling. Okay. First, let me tell you the motivation why. As stated, this is my motivation that I just want to compute arbitrary M2N scattering amplitude exactly at large n, n goes to infinity, keeping n by kappa, which is tube coupling lambda. Kappa is a Chern-Simons level, lambda fixed. Our initial motive. So this work I'm doing with Pranjal, Umesh, and Karthik, and probably will be putting up a paper very soon. And subsequently, I'm also going to talk about a work that I have initiated with Ritam and two students at IISER Pune. So my initial motivation, or our initial motivation to study this problem was simply naively we thought that we wanted to prove the duality. So that's the question that we started with, that how what can I compute to show that no problem.
We just started 30 seconds, right?
Okay. So I'll just restate. We want to compute arbitrary M2N scattering amplitude at large n, exactly in lambda, and our initial motivation was very naive. Maybe it was very naive, and we thought that all there is in a quantum field theory is computation of S matrices, and if I can compute arbitrary M2N arbitrary scattering amplitude at large n exactly, then I can show the duality. That was our initial motivation, because the reason that we need to compute all loop amplitude is because this is a Bose-Fermi duality is a strong weak duality. So if I am at the weak coupling at one side, I have to go to the strong coupling at other side. So we really need the computation at arbitrary loop exactly. So that.
So there's also the issue of non-perturbative
Yeah. That's right. So there are like, of course, there will be some things in the spectrum which will be left over. Like it depends on how do I take the limit. Like first I take n goes to infinity limit, then keep all the non-perturbative stuff. That will be states will be maybe scaling dimension of order n, and those if I take n to infinity, they may not contribute. But if I take the n limit later, it depends on like how do I take the limit. They might start contributing. Non-perturbative in lambda. So what we found, we solved to start with, we computed 2 to 2 scattering exactly. We solved a Swinger-Dyson equation, and we found no such non-perturbative terms. And probably yeah. Is there some reason that why we did not find any non-perturbative term?
Usually happens in the large n limit that the lambda perturbation theory has a finite radius.
Nice.
When you count planar graphs, they grow less fast than all graphs. All graphs grow like n factorial, but often planar graphs of a given genus grow like power with n. So at least in matrix models, that's
Yes.
these lambda expansions often have a finite radius.
But I see. In string theory, one can have worldsheet instant terms, right? But no such thing here. Right.
Sorry, I'm
Yeah.
really sorry to come in. So the claim is it's not an asymptotic in lambda for large n.
At least in the explicit
Yeah.
calculations.
And what are the explicit calculations? The S matrix elements?
Yeah, S matrix elements. We explicit computation that we did was 2 to 2 scattering amplitude for various theories like supersymmetric theories and non-supersymmetric theories. So I was telling about motivation why I wanted to compute. But that might be naive. That motivation might be naive, but we will keep that in mind. So that will actually give us a direction.
And I'm
Yeah,
really sorry
yeah.
again. So just briefly tell
Yeah.
about the theories. There are two groups with M and N.
No, so I'll say. So this I'm going to explain later.
Okay.
I just wrote to save time, but I was just telling about the motivation why we wanted to compute M to N scattering amplitude at exactly at lambda. So initially, maybe naively, we started thinking that we wanted to prove the duality, and if I want to prove the duality, Bose-Fermi duality, all I need to compute maybe all set of possible scattering amplitude and all set of possible scattering amplitude, and then check the duality. And here I need to compute exactly because it's a strong weak duality, so I need to compute exactly. So that was a naive motivation, which may turn out to be not correct. I think it's not correct maybe, because scattering things, perturbative things do not contain all the spectrum. Maybe there are like things which might go as order n, which I won't be able to see in this computation.
Okay, but if you can show that all scattering amplitudes are the same at large n, you'll have done a lot.
Okay.
Proof, not proof, that's...
Yeah.
Physicists usually don't prove things.
Okay. Okay. So yeah, but at the end of the day, so we will keep that in mind, and we'll see that this will help us actually proceed where we want to go. Okay. So
Sorry, what is this reservation? I didn't quite.
sorry.
What are you missing? You were saying that you might be missing something. What exactly?
Yeah. So at this moment, I'm scattering the fundamental particles, phis. But suppose there are fields which are say which goes as Siraj is not happy. Okay, so those I won't be scattering here. So those things I'll be leaving out. But sorry,
the external states are fundamental state.
sorry, say again.
The Lagrangian that you have written,
Yeah.
fields are in the fundamental representation.
Yes, that's right.
You will be scattering them.
Yeah, I'll be scattering. Sorry, say again.
What else do you want to scatter?
Let's say I have baryons, like which might be goes as n, whose scaling goes as n, say for example.
That's what I was going to ask. The things you're worried about would have either a mass or anomalous dimension, something
Yeah.
going like n, right?
Yes. Yes.
So maybe they may come as e to the minus n effects, or you think, I mean, you're strictly checking the equivalence at n going to infinity
Yeah.
as a function.
That's right. That's right.
So it might be that these
Yeah.
worries are less.
Yeah, I'm taking n to infinity fast in my computation.
So pair producing baryons or something as intermediates may be suppressed.
Maybe suppressed. Okay.
That reason.
Okay.
I'm wondering. I mean, typically solitrons and so on would be. Okay.
Okay. So, but at the end, okay.
Another thing
Yeah.
is that you get baryons as bound states when you do n of them with n of them.
Exactly.
Hmm.
They will show up as poles, but you'll never get that far because
Yeah, that's right. Or if you try to get it from just 2, then it will be some hugely suppressed form factor or something or the other.
Okay. So I have told you the motivation. Let me now tell you what are the things we have obtained. But before that, I want to tell you a little bit 5-minute summary of the background. So one of the reasons that we thought that this is possible, for example, if I take phi to the 4 theory, it's not possible to compute things like beyond, I know I have learned yesterday that there may be like up to 6 loop people have been able to compute. But it is not, in general, if I want to compute arbitrary loop, and arbitrary M to N scattering, it's not possible in a general quantum field theory. But what we observed is that for matter, the theory is coupled to Chern-Simons, where matter is in the fundamental representation. It can be boson, it can be fermion, or it can be like supersymmetric theories. What we observed that 2 to 2 scattering amplitude, we could compute exactly up to all orders in lambda. Okay. There are very interesting facts about it. First of all, what we noticed that the crossing symmetry was getting violated here. Second, the fact that it is exactly solvable. I'll come back to this later if I get time. But so this give rise to 2 questions. Number one why? Number 2, is it possible to compute arbitrary M to N? Does it also say that is it possible to compute arbitrary M to N scattering amplitude exactly or not? These are the 2 questions we want to actually understand. Okay.
And your second question is somehow roughly the question about whether the theory in some sense is integral.
Yes, and what I also want to we also want to understand this why this thing may be also connected.
Yeah, probably.
So these are the things that we want to understand. Okay. Now, in terms of computation, what we have done. So, so first of all, before computing arbitrary M2N at all loop, we need to compute tree level scattering amplitude at say arbitrary say 3 to 3 scattering before going to M2N, and we found that we did not knew that much, but we found that just computing for boson. So here, suppose I forget about the fermionic sector, just concentrate on the bosonic sector of this Lagrangian with some parameters set. Even for the bosonic sector, if I want to compute 3 to 3 scattering amplitude at tree level, it is like 25 or 26 diagrams. Lot of diagram. It's totally complicated, and just the tree level computation is really complicated. Going to the loop level is we did not even try that way.
Sorry, Sachin,
Yeah.
can I ask you, if you just take the purely bosonic theory,
Yes, yes,
your coefficients are still chosen in a somewhat particular way.
yes.
Is that going to be important for you? Or
Right now not, but we'll come back later. Yeah,
the choice here is
yeah.
presumably because of supersymmetry.
Yes. Yeah, so I just wanted to make a comment that this is what we computed and we failed because it was like a 25, 26 diagram even at the tree level, and it was not, we did not get anything intuition looking at this. So there was no way we could realize that there was no way we can go to the arbitrary loop order.
Were many of these tree level diagrams involving gauge boson exchange?
Yes.
Suppose you went to a gauge,
Huh.
like light cone gauge for instance, would that number 26 become much smaller?
Yeah, will become a little smaller for sure.
I actually can't think of so many graphs. There's one contact graph.
Yes.
Apart from propagator dressings,
Yeah.
give a couple of examples of such graphs.
So-
let's say I go to a light cone gauge.
Yeah, light cone gauge also you have this A3 square 5/5. That diagram is there. And let's say I have this kind of diagram at the tree level.
Okay.
Now, if I look at the colors, so suppose I 2, 3, 4, 5, 6. So the color structure of this diagram, So the color structure of this diagram is now this is 1, 2, this is 3, 4, this is 5, 6. Now I can interchange this, right? So I'll get 6 diagrams here.
Okay, you counted as 6, but it's one calculation, right?
Yeah, computation wise 1.
Okay.
Yeah, I agree.
It doesn't seem that bad, right, to calculate at 3 level or not?
No, it's not too bad. It's not too bad. But okay. Yeah, I agree. but
Sorry,
yeah.
out of this, but
Yeah.
light cone gauge is a good gauge to do these kind of calculations.
Yes, because at the end, yeah, go ahead.
No, go on.
No, at the end, if I am into the on-cell, if I take the on-cell computation, then actually, yeah, they are.
I'm just making sure
Yeah.
no subtleties or something.
For tree level, of course.
Of course, any.
Yeah. And
If
if
I.
light cone gauge is bad, then everything that's been done in these theories.
So what we did as that in our computation in one of our paper, we computed at one loop the light cone gauge result and the Landau gauge thing. Landau gauge had like 9 different diagrams, and light cone gauge had only 1 diagram, and they came out to be same, which was really nice thing. Okay, Siraj's comment, I agree that these are not too bad, but when you write down the expression like 26, it becomes really bad. So yeah, go ahead.
Really
Yeah,
sorry,
yeah, go ahead.
Can you briefly just in one sentence
Yeah,
say what
yeah.
was used to solve exactly the 2 to 2? There was some kind analog of a gap equation or something you solved
Yes.
in the end, right? If
Yes.
you remember?
Yeah,
That
so
was what you did.
yes.
A similar thing is not possible when you go to 3 to 3. That kind of a way of setting it up. You actually have to evaluate the diagrams.
Yeah, so let me give you like a 2-minute summary of what happened. So basically what happened was that we wanted to solve this, and I'll give a much better way of thinking
Okay,
later
I
on.
mean,
But yeah, it's a good point. So it will set up the reason why we needed to go to other thing. So then there were like diagrams. and I'm drawing these diagrams for a particular reason. And then there are a few diagrams, okay, I forgot right now. And then there were like a thing, this with this, okay. This thing I'm calling is as, full thing is identity. This is the identity, and this is what we are expanding, okay. This is a swing Dyson equation.
That circle is again blocked. Or
Yes, this block. So first of all, at the 2 to 2 scattering level, it was also necessary to understand the fact that these diagrams you have to take here. It was first non-trivial observation, which was made by Aharoni et al. For the case of fermion, it was much more easier though. Second thing, it was that if I look at this, there was a particular kinematics, K, P, and that kinematics is that only region, so the only way they could solve is that this contribution came out to be proportional to Q minus in the light cone gauge, and you set Q minus to 0, and this contribution dropped out, and then you can actually compute. So which was a very non-trivial observation. Now if I want to do it for the 6-point function,
I mean, they showed that.
yeah,
That is proportional to Q minus.
yeah, so 2 to 2 scattering, one can just compute this very easily, and they showed that it is proportional to Q minus, and you take Q minus to 0. So this don't contribute. Now at this will just go. From here there will be some constant. Q was here.
3 minus 1. I see. Okay. Yeah.
So there will be some constant term or something will come out, which I don't remember right now. But main fact that unless you set Q minus to 0, you could not have a swing Dyson here. Okay. Now doing this at the level of 6-point function, suppose I have.
You
Yeah.
cannot have, I mean, you don't know how to solve this.
Yeah, I don't know how to solve it.
You always have a Schwinger equation, right?
Like it should be possible that I should be able to write down, but is it so easy to actually formulate the swing Dyson equation?
I don't understand why can't we just replace all of that by some curly line?
All of them by some curly line in some other gauge?
In any gauge. I don't know. I work in this gauge, so there are no self-interactions. I don't want gauge goes on self-interaction.
Yes.
But then I'll just call that whole thing a curly line.
Yes.
And then I just have to iterate all these graphs, right?
Yeah, it won't be solvable, as you are right. That it won't be solvable. That
Meaning nobody has yet shown how to solve it.
yes.
You write down an equation.
Just to understand that cross-hatched is a code word for all these
All these
graphs,
graphs,
right?
yeah.
So a similar equation can probably be formulated. Of course, you have many variables, all the momenta, etc.
Yeah. So for the you see, so at the 2 to 2 scattering, I have only this, but at the 3 to 3, I'll have
Your
like
26 or
something like say order of 15 or something.
No, but if you could solve this,
Yeah.
you can solve that.
Sorry, say again.
If you can solve this for arbitrary momenta,
Yes.
I think you'll be able to sew them together to get 3 to 3.
Okay.
How
Yeah.
I mean, what
I think that every graph that you have will be
any
basic.
graph will be 2 to
will
2
be-
with a
Will be
solution.
this. Yeah, I think that every graph will be of this form.
Yeah. Yes. So here,
This will be the full 2.
here, and here. Yeah. So yeah. So why every graph will be of this form? Let me give you one simple expression. Yeah. So let's say I have this at one loop. I'm looking at say one loop, and let's say I have this diagram. What Siraj drew was this diagram is of this form. Okay. But clearly it lives over this. But the point is that this is 1 over n suppressed compared to this diagram. So there is no such, so all like these diagrams can be written as Siraj is saying this way. But
Then that's a
yeah.
tremendous simplification. I'm
Yeah.
sorry to interrupt
No, no,
you guys
yeah.
about the problem. Yes, but you mean okay, once you know the answer for Q minus equal to 0 or whatever, you can't using all the symmetries obtain it in general for a general chemical, no?
on cell, the point is that once I put this thing on cell, then I know for arbitrary kinematics. But here things are not on cell, so I really cannot use.
And also, because it's not on shell, there's very limited symmetry.
Hmm.
Because you're working in a gauge. And
Yeah.
the gauge moles Lorentz invariance.
Hmm.
So it's an off-shell gauge dependent quantity,
Hmm.
which doesn't have the full symmetries of the problem. That was the great thing about the on-shell quantity. The on-shell quantity has the full Lorentz invariance. And therefore you could get it for arbitrary
Okay, so this situation looks little bad, but there is something which you can do. Okay, Siraj, do you have a comment? No. Okay. Yeah.
Putting Q minus equal to 0, is it like you're finding it in a very particular particular kinematic situation?
Yes. So what you will do that we will set q plus minus to 0, then we can solve the Schwinger Dyson equation, and then we will covariantize, and then that is applicable to any other. Yeah, for any other kinematics.
And with q minus not equal to 0,
Yeah.
for the 2 to 2 you can set up an equation, but it's just impossible to solve that.
Yeah, as Siraj said, nobody tried.
It's a linear equation.
It's a linear equation.
If you use the right Russian, you might solve it.
It's a linear equation on all the momenta.
Yeah.
Yeah.
The unknown is a function of, let's say, 3 momenta, because it's momentum conservation. And it's a linear integral equation for these things.
Okay, so in all this game, one of the main thing is to come up with an answer for this. That's the main game also in solving. That I have an integral equation I can write down. Then one has to come up with an answer, and probably, as Siraj is saying, maybe if we try hard enough, we might be able to get.
So this q minus equal to 0 thing happens
Yeah.
when you put the external links on shell. Is only then. Is that
No, we compute. Yes, I mean like we compute for arbitrary off-cell stuff at q plus minus is equal to 0. Then the point is that once we put
Sorry,
yeah,
my question.
yeah, right.
I mean the fact that this comes proportional to q minus.
Yes.
That happens only when the
No,
external
no,
links are on.
no,
on
no,
on
no,
shell.
no, no,
So
off-cell.
then why can't you solve this Schwinger-Dyson equation for off-shell propagators? I mean, off-shell 4-point function.
It's just complicated.
No, but at Q minus equals 0, you can.
At q minus is equal to 0, you can.
And you can show these off-shell propagators to get the Bands diagram. No.
Yeah. You can. I think you can. There's one issue. The thing is that when you sow, these momenta are in your hands.
Yes.
But these momenta are in the middle and have to be integrated over everything.
Yes.
Okay. So this q minus equals 0 is a consistent condition. You can put an external momenta, but will be inconsistent when you have to integrate over them.
Okay, got it. Because the integral is over everything, including over q max.
Yeah.
Okay.
And the way this works is that intermediate leg coming out from the bottom diagram cross-hatched, that q minus also won't, or will it be? It will be 0, is it? If you impose q minus 0
Yeah, this
there,
one. Yeah,
will be
it will just run
that's
through.
why you can do
Yeah,
that,
it will just
but
run
you
through.
can't do it.
Yeah, exactly.
All right.
But so it turns. Okay, probably I'll tell it later. Okay.
Interesting.
Okay, so it looks little bad, maybe possible, but can we do little better? That was a question we were asking, and then one obvious place we should have started rather than the bosonic theory is that a supersymmetric n is equal to 2 supersymmetric theory. The reason I'll explain now. So we should have started n is equal to 2 supersymmetric theory, Chern-Simons theory coupled with the matter and fundamental. So here I have written down Lagrangian for supersymmetric theory coupled with Chern-Simons matter for n is equal to 1 supersymmetry. Okay. Now if I set W, this parameter, this is unfixed in the Lagrangian for n is equal to 1. If I set W is equal to 1, that reduces to n is equal to 2 supersymmetry. So n is equal to 2 supersymmetry fixes all the parameters. There is no, and I also would set masses to 0. Okay, I also want to set mass to 0 for the moment. Okay.
So you don't have the last two terms.
Yeah.
It's 1 minus omega.
Yes.
And you don't have the first
Yeah.
term and this term, so it's a
Yeah.
simplest.
Yeah. And what we are going to do right now, we will see that n is equal to 2 theory is important. But before going to that, let me tell you that this work is under progress. So we have not understood fully like what are the possible way, what to do with the n is equal to 1. But n is equal to 2 is a concrete case that we will be able to discuss right now. Okay. Okay, so for n is equal to 2 case, as I just said, W is equal to 1, and it becomes little simpler. It turns out that the 2 to 2 scattering amplitude, it does not get renormalized, not renormalized.
That means what, the tree level doesn't get corrected.
Exactly, tree level does not get corrected, and tree level shows that it is dual to each other. That's a very we observed, and it was really, we did not expect it, but somehow it worked out. And but this is only in the but there is a crossing symmetry violation, and what we found that there are other channels of scattering, like the S channel of scattering, where actually it gets renormalized.
Say again? I mean, it doesn't get renormalized?
In the T, so there are.
Or in the T and
Yeah,
Q
so
channel?
let me explain. Suppose I am interested in scattering amplitude of say all particle scattering, then it is the tree level answer is the exact answer.
Okay.
But suppose I am interested in particle antiparticle scattering, it has adjoint channel and the singlet channel. Singlet channel gets it renormalized. The way it gets renormalized, suppose this is singlet channel answer, and suppose this is the particle scattering, all particle scattering, it gets a factor of sin pi lambda by pi lambda plus cos pi lambda minus 1 delta theta. This is the way it gets renormalized. Okay. So for most of the scattering direction, which is like all particle or the adjoint or all antiparticle, this does not get renormalized, and the tree level answer is actually self-dual. So which is a much better starting point for our that if we want to show that there is a if I want to show the duality that all possible scattering amplitude goes to the all possible scattering amplitude, n is equal to 2 is the simplest place to start then. Okay.
So this SP is independent of lambda. Is that the point? Or
For n is equal to 2, yes. For n is equal to 2, SP is independent of lambda. It turns out that this relation actually holds true for n is equal to 1 as well, but this becomes totally complicated. Even for boson, this relation holds. Even for fermion, this relation holds. So this is like a universal relation. So n is equal to 2 is a very natural place to start doing the computation. And before going to the little bit of details, let me first tell you some features about n is equal to 2. N is equal to 2, if you look at the Lagrangian, W is equal to, say W is equal to 1, or don't say W is equal to 1, but you look at the fermionic sector of the Lagrangian. Fermionic sector of the Lagrangian, just the way there is fermion, it is same in n is equal to 1 and also same in the pure Chern-Simons theory coupled with fermion. Okay. So any conclusion that I get for
Sorry, this is
yeah.
now you're doing what value of W?
So n is equal to 2 is W is equal to 1. But I'm saying, yeah, go ahead.
Sorry, you still have that psi bar phi, phi bar psi coupling.
Yes, but I'm saying let's concentrate only at the tree level. At the tree level, if I look at the n is equal to 2, just the fermionic sector, then the tree level scattering amplitude is going to be same for n is equal to 1 or the fermion coupled to just fermion coupled to Chern-Simons. Okay. So any conclusion that I draw from n is equal to 2 supersymmetric theory will be for the tree level will be applicable to the those theories as well.
Okay.
Okay.
Tree level.
Sorry, I'll just get a water. Yeah. Okay, so
what are we saying for fermion external legs?
yes,
W equal to 1 is not playing any role. Is that
yeah, it does not play any role.
That's not clear from looking at the Lagrangian.
But just for tree level.
Just the tree level.
It's for tree level because that psi bar phi, phi bar psi won't enter at tree level.
Yeah.
Because your two phi's.
Yes. So
For fermion external legs, it's
yeah.
not making any sense.
because all the internal lines will also be fermion. It won't be any.
It's a consistent truncation to setting phi.
Yeah.
What is the interaction? I can only see kinetic.
Gauge.
That's what. That's the gauge. Okay. Okay. Now, first thing, what we checked is that, as Siraj pointed out, can we write down the First thing, the brute force way we started doing is that we just computed 3 to 3 scattering amplitude by doing Swinger Dyson equation, and it turned out that it was actually tree level was the exact answer. Okay, but we were naive. Yeah, go ahead.
In what case n equals 2?
N is equal to 2. We were a bit naive and we spoke with Siraz and he pointed out a mistake. So right now we are redoing the computation. But I'll tell you a different, little bit of different story. So, but hopefully 2 to 2 scattering do not get renormalized, but we are hoping that 3 to 3 will not also not get renormalized, but we will know it very soon. Okay, so
But sorry,
yeah,
let me just
yes,
ask another
yes.
question, please. I mean, you made a statement about, we're not talking of n equals 1, right? Or n equals 2.
Right now we'll be just talking about n is equal to 2.
Okay. N equals 2, you want to look at 3 to 3.
Yes.
2 to 2 you are sure is not renormalized.
Yes.
That's your rule.
Hmm.
You want to ask whether it's true for 3 to 3.
Hmm.
But at some point you brought in n equals 1, so I got confused in the. You're
Yeah.
not talking of n equals 1.
No.
Okay.
Yeah.
And you're going to examine m to n for n equals 2?
Yes.
Okay. fine.
Okay. Now, what do we want to do is that we want to introduce one more element into the problem, is that which is well known, and unfortunately I did not know much about it. We did not know much about it. Is that so suppose people want to compute higher point amplitude. One way to compute is through BCFW relation. But it's not true that arbitrary theory will show some BCFW kind of relation. BCFW relation is just states that any higher point amplitude can be constructed out of lower point amplitude at the tree level. It is clearly done at the tree level, but at the loop level, people have studied some things, which will come back to, which I'll come back to later. Okay. So suppose I want to compute for the n is equal to 2 supersymmetric theory, a tree level 3 to 3 scattering, and
clearly aware in which channels in 3 to 3 there will be no renormalization and in which there will be renormalization of this kind or something.
yeah, say there is no renormalization that we have to compute still, but the point would be suppose I take all the particle scattering. And that's our general observation at 2 to 2 scattering. We noticed that at the all particle scattering we did not find any renormalization, and hopefully that's going to be true. And one thing also one has to notice is that so 2 to 2 scattering amplitude, why it did not get renormalized was that suppose I compute this diagram, this was order 1 over n, and the singlet channel answer actually was order 1. Now suppose I look at T minus T dagger, this is T dagger. If it is order 1 over n, right hand side goes over order 1 over n square. So up to order 1 over n, T minus T dagger is always 0, and all you have to do check if that's like a like this is true or not. So it's a very easy to satisfy. But suppose yeah. Sorry, what? Yeah. No, yeah. So, sorry. So the point was that this was consistent with the fact that it was not getting renormalized at the tree level. This is, we know that T minus T dagger is always 0. That's the property of the tree level. Okay. Yeah.
So is it a correct statement that whenever there is a singlet channel
Yeah.
running in between, then it will get renormalized? It might get renormalized. Whenever there is no singlet channel, then it will never be.
No.
It's not.
No. It's, you know, I think the correct statement is that it is about Arnav-Bohm phase. So whenever you have an Arnav-Bohm phase in exchange of anything that is non-zero, you will get renormalization. You will have to. Now, you see, suppose you've got three particle scattering. What you will do is to take any two of the particles you're scattering and couple them into some group theory representation. Then you will take that composite and the last particle and couple. And the question is, in these couplings, is there an Arnav-Bohm phase? Now the rule is that the Arnav-Bohm phase is Casimir of the first plus Casimir of the second minus Casimir of the composite divided by T. Okay? So whenever you are doing a coupling such that that is non-vanishing at large N, you should find it. Okay? So for instance, when you couple, if you have particle-particle antibodies, let's say you couple the two particles to symmetric. That coupling has no Arnold bound phase. Then you take the symmetric and couple to anti-fundamental, and you get from there a fundamental. That will have a. So more correctly, the rule is every time there's a contraction between indices in the coupling, then you should expect it.
Meaning initial three particles, if you can make a singlet out of all
No. You see, so suppose I took two fundamentals and an anti-fundamental.
Yes.
One thing you can do is make a representation which is fundamental, like, you know, a representation like this.
Yeah.
Okay? But you've not contracted with the fundamental and the anti-fundamental. This will not have, will plausibly not have been. You'll have no book. But if you take a representation where you contract the fundamental index with the anti-fundamental, you're still left with a fundamental. It's a much smaller representation than the maximum you can get. That will always have an Arnold phase, and so therefore we have to have it.
But I thought, okay, fundamental, what was this, if you can just do this example, two fundamentals going to?
No, so let's do three particles.
Three particles captured.
So fundamental, anti-fundamental, going to fundamental, anti-fundamental.
Gotcha.
Okay? Now this thing has many channels of gap. You can take the fundamental, anti-fundamental, and you have to couple them in every way you can in group theory. So we have choices, take the choices, so we couple the two fundamentals first. So you get either symmetric or antisymmetric. Now you have to take that and couple to anti-fundamental. So when you do that coupling, you can get these big representations, which are essentially products of anti-fundamental and symmetric. You know, that kind of gap. Or you can get a representation where you contract one of the indices of the symmetric with the anti-fundamental index, and you're left with just a fundamental. The first coupling will have no Arnold bound phase in the large element, and so plausibly is not renormalized. But the second coupling will have an Arnold bound phase. You can calculate it. Okay, and there has to be. That's why Sachin was saying if you start with three fundamentals, then there's no possibility of doing any contraction, and so plausibly we'll never get rid of it.
Okay. I don't need to explain anymore. Okay. So.
And you couldn't understand the lack of the non-renormalization just through some souped-up holomorphy, or if you looked at the diagrams in superspace or something, that it wasn't any manifest reason.
Yeah, but it was getting renormalized in one channel, so I don't know.
It's a mild renormalization.
Mild.
You just put in some factors,
Yeah.
right? I mean,
Probably.
I'm just asking.
No, that's a good question. Yeah.
Particle channel. There was
No, but
manifestly supersymmetric waves.
no, but we have probably if I get the time, we have noticed little more symmetry into the game, and probably that will help. I do not know whether that will help or not.
In our paper, n equals 2 is an afterthought.
Yeah.
We did the whole n equals 1 calculation,
Yeah.
and we said w equals 1. Oh, look. Particularly focus on n equals 1.
Yeah.
Try this game.
Yeah, actually, one of the questions that we, so we do not have at this moment, but it may not be like maybe we have to look at the symmetries much more. Okay, so let's now focus on the supersymmetric theory. Yeah.
Just one more comment about that. You see, non-renormalization at finite n is impossible. Because, you know, scattering amplitudes in general are never non-renormalized because of unitarity. If you've got a tree amplitude, since the square of the tree is the cut of the loop, it's usually just an inconsistent statement to say that the scattering amplitude is tree length exact. However, at large n it can happen. If the tree amplitude is 1 by n, then the loop amplitude is 1 by n square, and that's, you know, this cut is 1 by n square, so you don't care.
But it can happen, as Siraj is saying, but it is possible that like n is equal to 1 or other theory, it gets really renormalized in a totally complicated way.
Yeah.
For n is equal to 2 spatially, it just goes to tree level. Okay, so I just started with the BCFW. Again, what we did is that we just looked at the bosonic sector of this and tried to compute the tree level scattering amplitude and tried to check if it satisfies the so I'll come to what exactly is the detail, but let me tell you the result that we have got. It turned out that if I look at the boson or the pure fermion amplitudes, the usual deformation, the simplest deformation which I am going to define, does not show that there would be, it says that there is no BCFW kind of relation, okay. That was our first conclusion. And then
Sorry, what's the statement?
statement is that if I look at naively this psi bar psi, psi bar psi, psi bar psi, or replace it by phi's, there is no such thing as there is a, and suppose I choose to deform, which I am going to define right now, under usual BCFW deformation, they do not behave well at infinity, which is the basis of BCFW recursion, which I am going to show you right now. And similarly for the boson. Okay. So we thought maybe it is not possible, but it turns out that somehow supersymmetry plays really a nice role, and it turns out that supersymmetric amplitude as a whole has this kind of that BCFW recursion, which I am going to tell now.
Supersymmetric amplitudes in large n? Or
Yes, large n. But at the tree level, I suppose it does not really make a difference,
this is
much
all
difference.
tree level.
Yeah, at this moment, all tree level. Our hope is to go to the all loop, is if the tree level does not get renormalized. But I think at the end, if even it gets renormalized, we will be able to compute, because we could compute 2 to 2. So I don't see any barrier in computing arbitrary m to n, but at least 3 to 3. But yeah, we have not done yet. Okay, so.
BCFW has some restriction about helicities of external legs.
Yes. So for our case, all external legs will be just fermion or boson, because gauge fields are not there externally, because it is Chern-Simons theory. So external, there is no on-cell external gauge field. So all thing will be either boson or the fermion.
And in 3 dimensions, there's
Yes.
no ambiguity as to fermion polarization.
Unique fermion polarization. Because it's on-cell, you just get to, yeah, that's right. Okay, so now let me start with the 2 to 2 scattering amplitude, then I'll go to 3 to 3 scattering amplitude. Okay. 2 to 2 scattering amplitude. But before that, I need to introduce a bit of little bit of.
You tell us about this BCFW.
Yeah.
I once read about it.
I might not even have one there.
Yeah, I'll tell. But how much time do I have?
That's time. Let's say half an hour.
Half an hour.
I mean, it could be more, right?
Okay.
Sachin, a question.
Yes.
So the question. So what is the Schwinger-Dyson equation for? Can you write down the Schwinger-Dyson equation for 3 to 3 in terms of 2 to 2, or what is the extra piece if you try to write down the Schwinger-Dyson equation?
You mean the okay? So okay, Siraj was explaining. Let me try to explain this. So yeah, as you are asking, so let me do the 3 to 3 scattering amplitude, and where Siraj drew. Can you see the board, Loga? Oh.
Yeah, okay. So this is one contribution, definitely.
Yes.
Is there any other contribution? Is there a contribution which have to take into account in the vertex? Is there a
Yeah.
Is that the question?
Yes. Okay. So suppose I'm at the tree level doing tree level scattering amplitude in the Landau gauge, then there is one such diagram as this.
But if you work in light
Yeah.
gauge,
Yeah.
that
So
would be nothing.
exactly. So the point is that in the Landau gauge we could not even go beyond one loop, so we will be restricting to the light cone gauge, and this kind of diagram will just go to 0.
Mm-hmm.
And all the diagrams will be left will always be of this order or of this kind. And the one way to see this, I try to explain it, but let me try to explain this. This is of this kind, okay? For example, one such diagram. This is order. If I count, this is order 1 over n square.
So yeah, right. So Sachin, just the statement
No, but yeah, that's a good point. But look at this. That these legs are off cell. These legs are off cell. Now, had this leg been on cell, it would have been the case readily, as you are saying. It would have been the case that this is tree level exact. But the fact that these are not on, these are off cell, so it's not immediately clear. But let me tell you that what we did is that we naively thought there is not this thing because we were drawing in a different way. And it turned out that these were like, it was not getting renormalized. But with this loop, we are still doing. Probably it will not be renormalized, but we are not sure. Yeah,
Sorry,
go ahead.
one more comment. If you were in 4 to 4,
Yes.
then there would be genuinely new diagrams.
Oh, really?
I think so. Because if you're doing 4 to 4, if you did this, then you could have an exchange between this line and this line that is not part of any of the.
But Siraj, I think again those will be 1 over n suppressed.
I don't think so.
Oh, you don't think so? Okay.
You could dress this.
Huh.
This is all plain.
Yes, but Siraj, once I have this, I need one more loop because this is 1 over n.
What do you mean? I mean, this is a planar graph. It's as planar as the other graph.
Yes, but this is also as planar as the other graph. I do not know. Maybe you are right. I'm just asking or just making a comment. This is as planar as the other graph, but this is 1 over n suppressed compared to this.
So, sorry, but
Yeah,
in
no
this
problem.
graph,
Yeah.
I can just calculate the powers of n of this without this. I don't think there's another.
Okay.
It's just a
Oh, you are
feature.
saying yeah, there is a loop here, so probably that will play a role. Yeah.
I think this is as
As good.
good as.
Hmm.
The 3 to 3 had the property
Huh.
that if you have exchange between any two lines, it can be absorbed into those two.
Yeah.
But that's not true for.
For this.
And it still survives in large.
I think so. I haven't thought carefully, but I think.
Okay.
But just one more comment that yeah maybe it or be possible, but one more comment is that still like Siroman very recently computed J0 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 4 point of J0, and these diagrams are very much similar because I just saw this, it becomes like J0, and he could compute it exactly, but though like there were a little bit of probably it is, but yeah, the general thing that tree level is not going to get renormalized, that may not be true. That
No, it
I'm
may
not
be
saying.
true. It may be that this is needed to make that. Who knows?
Huh. Yeah.
I mean, this is just a technical observation.
That's right. I see.
You know.
Interesting.
But I think that one is suppressed because there'll be 1 over kappa cube factor coming from the extra propagator and the 2 extra vertices, and you have only introduced 1 loop extra on the right hand side.
We should work that out carefully.
But this is like 1 over
Classic
kappa.
fishnet diagram. I think I would be very, very surprised if this is surprised. This is the kind of thing we saw.
You can certainly draw it. I don't know. You can draw it.
I don't
Yeah. No, here I think yeah, this is just 1 over k, and there is 1 more extra loop, so it's not suppressed, I think. Okay, so yeah, so let me now concentrate on the tree level n is equal to 2, and
So you're going to do, if I understand, 3 to 3, n equals to 3 level.
yes, say for example, yeah, so before going to as Siraj mentioned here, let me give you one more. So BCFW I'm going to show, but we also observed the following, that with Ritam and some student at IISER, we observed that 2 to 2 scattering amplitude for n is equal to 2 have this dual conformal symmetry. Okay, so why it might be important is that, so for n is equal to 6 ABJM theory, or n is equal to 4 super Yang-Mills theory, what people have shown is that there is a dual super conformal invariance here, and So we have shown dual conformal invariance here. We did not get time to actually to super conformal, but probably it will work out. But what they have shown that n is equal to 6 and n is equal to 4, there is a dual super conformal invariance, and that symmetry extended to Yangian symmetry. Okay. Let me explain what is Yangian symmetry in like briefly as possible.
Superconformal means
Yeah.
The conformal symmetry is in momental space.
I'll explain. Yeah. Sorry, I should explain. So suppose I'm looking at 2 to 2 scattering. So P1, I introduce a new variable. P1 is equal to x1 minus x2. P2 is equal to x2 minus x3. I'll just write for a reason. P3 is equal to x3 minus x4. And P4 is equal to x4 minus x1. Such that summation over Pi is automatic. Now, if I write down my amplitude in this variable, it turns out for this theory, in this variable, they behave like a space-time like they emerges as this superconformal invariance, and they behave like a space-time variable. In the sense that suppose I compute.
N equal to 4 thing was Aldrin Alderson.
Yeah.
And then the similar thing has
Yeah.
been done
For n is equal to 6. And the reason, so if, okay, first let me tell you okay, so now in the x variable, suppose I am interested in the 4-point scattering amplitude, and let me compute arbitrary loop order, it will turn out that S4 will behave with whatever, suppose you are scattering fundamental particles, so they will have some particular weights under scaling. And so there will be some xij to the power usual factors that are there, h minus hi, something. And then it is determined up to a cross ratio of u and v. Okay. Dual conformal invariance tells you up to this.
That's very interesting.
Now, what they in addition they understood is that it goes over to Yangian symmetry. What is Yangian symmetry? Yangian symmetry is a infinite dimensional symmetry. What it does, it takes the super conformal generators as the level 0 generator.
Sachin?
Yes.
This is for all these statements of this dual conformal invariance is for mass equal to 0.
Yes. Yes. Okay. It might be my knowledge is little less, but whatever I looked at, all they are talking about mass is equal to 0. Yeah. Massive case clearly it's going to break, I think.
No, I'm asking about the result that you guys have. Is
Yeah.
it for n equal to mass equal to 0?
Yes. N is equal to 2, mass is equal to 0. That's right.
Okay.
So the non-renormalization
Huh.
of the 2 to 2 scattering
Was
true even at finite.
even at finite n. That's right.
Finite mass.
So probably all we have to do is to associate some mass to some scaling, and maybe it will work out. Not sure, but one has to look up. Yeah. Okay.
But the conformal invariance, of course, you won't have that or dual, right? Once you have a massive theory.
But going to this variable, I mean, like conformal invariance just emerged, so it's not clear to at this point. Yes.
Scaling with momentum, you would break once you have a mass, or am I thinking wrong? In my case, position scale. Seems like that, like propagators, k square plus m square. How can
Yeah.
that have any invariance?
Yeah.
Rescale.
That's right. Okay.
When you check this ABGM dual superconformal invariance,
Yes.
this you check from some explicitly computed answer. That there is an answer and you can do this transformation and see. But I thought you will have that statement that the people who compute ABGM thing, they haven't computed it correctly because they don't get either unitary or these.
No, so
and
it's
so on. What do they check this on?
yeah. So one of the things that they check is the tree level scattering amplitude.
Just the tree level.
So they start with the tree level, but then they write down like the loop level answers, loop level intrigants in terms of this, and then they claim that this symmetry is going to be there. To be honest, I know explicitly computation for the tree level. I do not understand yet the loop level, which is I'm going to look up very soon though. Okay. For our case, situation is a little better because the tree level is the exact answer. So if it is there, so it's going to be there. Okay. So now, what is Yangian symmetry? Yangian symmetry, does is that suppose I call it Y, it's an algebra, infinite dimensional algebra. The level, I'm calling it a level 0. Level 0 is associated with the conformal symmetry, dual conformal symmetry, okay? Conformal generators. Level 1 will be product of these conformal generators. And then there are some particular relation that this generator has to satisfy. These are called Serre relation, which is I don't have it written here, but it's but you can look up in the paper of Witten and Dolan and Napi. There is a very nice discussion. And the basic point is that if you can show that your theory is invariant under Y1, then using the algebra, you can show that your theory is invariant under all the rest. Okay? So the only non-trivial thing would be to show that it is invariant under Y1. Okay?
I see. So why not are many generators and Y1 also are many generators?
Yeah. So why not, for example, will be like 15 generators in 4 dimensions, say, for example. Y1 will be like product of these things, which can be very complicated. But people have done it. Now, the point of Y1, how can it help? Y1, I would, yeah, go ahead.
Okay, so product meaning some complicated kind of product, because normally if you have Lie algebra generators.
Yeah, it's a complicated product, and then it has to satisfy some algebra, which is called some relation. It's a more complicated version of these identities. Sorry.
It's like
Yeah, yeah. Now.
And for all values of the coupling in N equals for SYM, they have the symmetry.
I do not know at this stage, but I know for tree level for sure they have, but probably it is there. Yeah, I think people have done it using some spin chain something, which I do not know at this stage. Seriously. Okay. But how can it help? Suppose I can show that there is this symmetry. How it can, because I have a tree level answer, I can really check this. Suppose I don't have an answer, say for example, how it can help is that Y1 will act on this and it will give a differential equation on FUV. That it has to solve, which is much better than the conformal symmetry, because there is a check that you can, and probably I don't at this moment know that equation probably will be like constraining enough to solve FUV.
You're assuming that the theory has the symmetry and then you try to find the amplitude.
No. I'm saying in the case where there is this amplitude, I'm stating a statement that I'm making a statement that suppose you can check suppose there is a check that there is this Yangian symmetry into the system. Suppose you check somewhere, then how it can help you in computing like the scattering amplitude. So conformal invariance fixes up to this, but this symmetry will give you more constraint on the form of the FUV that you have.
So first let me understand what constraints you get from this dual conformal.
Yeah.
So an arbitrary scattering amplitude is a function of S and T, two real variables. Here in your first form, it also looks like you have a function of two real variables.
Yes.
So I'm not seeing where the constraint is. I would have expected that if you had a non-trivial constraint, you would have a function of fewer variables.
Yeah, so here dual conformal invariance really it just says that it has to be of this form, which is not really a big constraint, as you say.
What I was asking is, given that the scattering amplitude is some function of S and T,
Yes.
can you tell me what constraint on that function of S and T that statement is?
Here?
No. The first one.
There will, you are asking if I associate S and T directly with U or V directly or not, right? Is there a relation?
Yeah.
Yeah.
Are U and V independent real variables?
Yes, independent real variable. It's just constructed out of like I have x1, x2, x3, x4.
And on shell, are they independent?
On say are they independent or not?
Is this a function of two variables or one variable? If it's a function of one variable, it's quite a statement.
Otherwise, it's not a
scattering
statement.
amplitude
Yeah.
are functions of two variables. If it's a function of two variables, I don't see what the statement is.
Yeah. At this level, not much. At this level, I think.
Are you sure it's a
yeah.
function effectively of two variables on shell?
I do not know at this stage.
So what's the point that under Y1 this F gets further
Yeah.
restricted?
Yeah.
And
Yeah.
It gets determined? Is it
I'm sorry, I'm making a statement which I have not yet started computing, but I'm just giving you I'm just telling you that how these symmetries can be helpful. Okay, that it really gives you something more on FUV, and for our case, the point would be that for our case, FUV I know for n is equal to 2 scattering amplitude, which is at the tree level. All I have to do is to put that differential equation and check if it satisfies or not. So that is amount to saying whether there is a Yangian symmetry into the system or not. For our case, it's really not a 2 to 2 scattering, it's not really helping much because I know the answer. But at this moment, these are just observation. I do not know how it is going to feed in into the bigger picture where I really want to go to the higher loop, higher point amplitude, which but probably this might play some role because. Okay, my knowledge, as I stated, is not that good at this moment, but the point is that somehow this is related to the integrability of the system, and if solvability and integrability, these are like interchangeably people use, and probably these symmetries might be able to help us in understanding the fact that it's really I should be able to solve. Probably, I do not know. But at this moment, how this symmetry is going to play a role, I do not know. Maybe this is also going to tell us why this is not getting renormalized or something. Those part I do not know yet.
So
Yeah.
the border entities or equations that y0 will impose
Yes.
are first order, if I understand, in your x variables.
Yes.
Y1 will probably be second order.
Probably.
But independent, it's not squares of.
No, it's independent. But rest y3, y2 on, those are all dependent. If you know these two, then others are automatic. Sorry, my statement were just making statement but showing not much. But I'll show you more concrete thing now. Okay. So
So
yeah.
if I understand, you are going to check whether 2 to 2 satisfies also the.
Yeah. Okay. So now I'll go. I'll not work into this variable, but I'll just go and work into the momentum space. Okay. And I'm going to do the supersymmetric amplitude. N is equal to 2 supersymmetric amplitude. Okay. For that, I need to spend like 2 minutes, a few minutes telling you about the on-cell superspace formalism a bit. So the simplest for n is equal to 2, the algebra is q bar alpha beta is equal to p alpha beta up to something, and then q with q is 0, q bar with q bar is 0, and then you have also R symmetry, etc., etc. Okay. Now, one way to solve these equations is that introduce q alpha is equal to lambda alpha del del theta and q alpha I del del theta I, and q bar I alpha is equal to lambda alpha I theta I. Okay. It turns out that it's a good choice, and yeah, so sorry. So suppose this is like suppose I have scattering amplitude, then this goes to 1, 2 to n. When I say my supersymmetric amplitude has to be invariant under supersymmetry, I need to apply q summation over I acting on S has to be 0. Okay. So n is equal to 1 version we developed in our paper with Siraz and other people. But for n is equal to 2, this n is equal to 2, one can actually, one way to do n is equal to 2 is to start with n is equal to 1 and go over to n is equal to 2. But that gives it's a possible thing, but it's a little more complicated. But directly doing n is equal to 2 in this language is much more easier. Okay, and this was introduced by some on some like long back paper by maybe Nicholas Bizot or some people while doing ABGM theory. Okay. Now, it turns out that this kind of choice actually solves my
What are lambda?
Yeah, I'll say. So yeah. So for I'm taking mass is equal to 0, and p slash u is 0, and p slash v is 0. This for massless case, lambdas are just u's. These are the solutions.
Is it standard? Are you writing every 4 vector as in terms of lambda alphas or something?
Yeah. So here all these are like 3 dimension. So I have only two column thing, and p alpha beta will be written as lambda alpha lambda beta. These are just solution to one. Yeah.
And how does the theta? What is your on-shell solution?
Sorry, you mean the phi? What's the on cell phi? Sorry, go ahead.
Yeah, what's the on-shell?
Yeah, okay. What was the on cell? Yeah.
This is an on-shell superstructure.
Yes, exactly. And I'll write down A, which is like A alpha theta. And A dagger, I'm going to choose is that theta A dagger plus alpha dagger.
Where A and alpha are the bosonic and
Bos-
fermionic
yeah.
solutions,
Yes.
A dagger and alpha dagger.
Yes.
Uh,
Okay.
This uses masslessness.
Yeah, this is a masslessness. Yes. This here, right now what I'm going to restrict is massless case. For massive case, it turns out, we have not thought much, but it turns out a bit more complicated because lambdas becomes. So, yeah, why, at the end, I'm going to express all my amplitude in terms of lambdas. Why is it useful? This spinor helicity formalism, why it is useful? Because suppose I have an amplitude which is like a P1, which is a function of all the external momenta, P1, P2, P3. In the momentum space, it's not like, although these are on cell, P1s are on cell, all the external particles are on cell, but it's not manifest in the amplitude. But if I express P1s in terms of lambdas, it becomes manifest and the amplitude simplifies. So it's a one nice way to express. Okay. So we'll be actually doing that's we'll be doing in the spinor language. Okay. Now let me immediately start doing the four-dimensional, 2-to-2 scattering amplitude.
But in this case, that's the same as expressing it as a function of S and T. There's no polarization in this, yeah?
Sorry, S and T meaning?
Mandelstam variables.
These things?
I'm saying that you said that if you express it in terms of momenta, you're not putting in the on-shell lecture. But if you express it in terms of Mandelstam variables,
exactly.
you are.
Yeah, exactly. But say I'm into the 3-to-3 scattering amplitude, then I have like the many Mandelstam variable. It may not be too much efficient.
Yeah.
Okay, so let me immediately start constructing the 4-point scattering amplitude. So 2-to-2 scattering amplitude, I need that both Q acting on S and Q bar acting on S has to be 0. Okay. Yeah.
What if one of the external line is bosonic? Your lambda alpha is
Sorry, say again.
if one of your external line is bosonic,
Yes.
how can you put lambda alpha? There is no.
Yeah, just give me 2 minutes, it will be answered. Okay.
Lambda is defined by P alpha, B beta, lambda alpha, lambda beta.
Right, so it's not tied to
Oh, sorry. Yeah, okay.
That was Shiraz's point.
Okay, sorry. Okay. Now, QS is equal to 0 and Q bar S is equal to 0, that I have to solve. Now, the point is Q bar is a linear in theta. Okay. Here,
Lambdas are they real or complex?
yeah. No, it's not complex. You can show in 2 dimensions. I can always choose sigma, which are real or imaginary. So these are either real or imaginary.
So there's no ambiguity. Right?
Yeah,
No
the-
phase ambiguity.
no phase
Up
ambiguity.
To some plus minus.
Up to plus minus, yeah. Up to some factors of I. No, up to some plus minus. Up to some plus minus. That's right. That's right. And that might be actually, yeah. So now all I have to solve is Q bar acting on S is 0. Now Q bar is multiplicative, okay? So it's going to act as a multiplicative. There's one more thing though, that if I construct R symmetry generator in this language, R symmetry generator becomes theta del del theta minus half. Okay? And my theory, if I act on R with the R symmetry, it has to satisfy R symmetry. So R acting on S is equal to 0, which implies summation over theta I del del theta I is acting on S is equal to n times S. Okay, n is the so for 2n scattering amplitude, this is n. Okay. Now this clearly says that S has to be for 2n scattering amplitude. S has to be like order on theta to the power n. By theta to the power n, I mean like theta 1, theta 2. So theta 1 square is 0, or all that, because it is a Grassmannian. So it has to be a product of all the thetas up to order n. Okay. Now for 2-to-2 scattering, we immediately see that it has to be order 2 in thetas. Okay. And for 3-to-3 scattering, for 3-to-3 it is order 3, and for 2-to-2 it is order 2. Okay. Now if it is order 2, in Q bar, one solution.
So the R symmetry is U1.
Yes, R symmetry is just U1 symmetry. Now one solution is just S is some function times Q bar square. Okay. So Q bar in my notation is summation over I. So Q bar I'm saying summation over Qi. Okay.
Wait, so help me understand how the bosonic. If I say the bosonic particle has R symmetry 1.
Yeah.
Fermionic particle has R symmetry
1. Everything is just 1.
The whole multiplet has 1.
Yeah.
But R symmetry should commute with source. Because there's an n equals 2.
Yeah.
I see.
In your units it's half, right? Everything seems half.
Everything seems half.
Is half, there's a plus
Yeah.
half.
Okay, so S, now if I compute with Q acting on S, this is 0 by the fact that summation over P. So Q bar is anti-commutator is P alpha beta. Now suppose this is summation over Q and summation over Q bar. Q acting on this up to like momentum conservation, this will be 0. And Q bar is automatically 0 because it's like a Grassmann variable. And it turns out this is a solution. Okay.
This is so elegant, beautiful. This is your n equals to 2, 2, 2.
Yeah. So this was done like earlier, but our so you see that it is automatically 2, 2, 2.
What do you mean for your n equals 2 is 2, 2, 2, 2?
Yeah.
It's just kinematics.
Kinematics is done earlier.
I mean,
good.
so this meets your conditions, but that it is the only solution. Or that it
Yeah.
is-
So I'll explain. Yeah.
But F4 is undetermined.
F4 is undetermined.
But it is clear that up to F4 it
Yeah.
has to be this.
Yeah,
no?
yeah,
That is
yeah.
clear. I mean, what you show is that it solves these, but you can reverse it.
Yeah.
Okay, fine.
Now, actually, we made an observation in our paper is that if I compute so you see there can be like 2 to the power 4 number of amplitude, boson fermion, like 16 amplitude. And here I am claiming out of 16, there is only one independent scattering amplitude, which is the power of supersymmetry. But if what we did in our paper is that n is equal to 1, there were 2 independent solutions. And if I set n is equal to 2, it turned out that 2 become related and it become only one scattering amplitude. Okay.
But this way is much more elegant.
This way is much more elegant because it just directly gives me. Okay.
And there's no analog for n equals 1.
The analog for n equals 1 is more complicated because there are 2 independent scattering functions. Will that be worked out?
I mean, can you do it like this?
Yeah, we can do it a little better. Yeah, you can do it a little better than we did, I think. But this general formalism works well when the number of supersymmetries is even.
Yeah, exactly. Like n is equal to 4, n is equal to 6, this way. Otherwise, what you will have only Q, and then Q will be function of.
You're in 3D, so
Yeah.
theta is real. Maybe is this related to that? You don't have a phase. Like I was thinking 4D n equals 1. That's really what you
Probably,
don't have
probably.
good R symmetry. You don't have good R symmetry with n equals 1 and 3. Do you? Or you do?
No, you do.
It's a U1. It's not a U1.
No, there's no asymmetry.
So maybe that's why
It's SO1.
It's SO1. no?
Yeah.
So maybe that's why.
I suppose that's right. Yes. However, n equals 3 is also tough in 3 dimensions, even though there's an SO3 also. This has been analyzed by people, right? I mean,
Sorry?
I remember Yutin Wang telling me about it.
Yeah.
That in addition to solutions like this
Yeah.
for odd guys, this is not the full solution.
Yeah.
When n is odd.
For in odd, for example, I will have only this, and this will be there will be also linear in theta. So del theta and theta will be here at the level at 1 Q, and then it becomes solving becomes a little more tricky, but we solved in our paper.
I mean, you can do it, but not in this.
Elegant way, yeah.
Beautiful.
So there, that the fact that there are 2 independent functions came out after the after we really put like n is equal to 2, we had to put extra on n is equal to 1, and
That's
then come out.
really, yeah, sorry.
Yeah. But this thing about putting a theta with a dagger rather than with alpha dagger.
Yeah, that made the
will
change.
help even in our situation, right?
Yeah.
It'll make our identity operator, which is quite complicated.
Yeah,
will become a
exactly.
delta function.
Yeah, will become delta function. That's right.
Okay, this really suggests that, I mean, of course, that doesn't mean, but you do 3 to 3 or m to n and n equals 2 first or something. I mean, yeah, that's such a
Yeah. So we actually spend a lot of time understanding from n is equal to 1 point of view, and it become little, even 3 to 3 become little complicated. But once we understood this way, it become little easier. Okay. Okay. So now all I have to determine is F4. Now I can actually compute at the tree level just this diagram. Say this is the amplitude, and let me say W is equal to 1. Yeah.
I'm really sorry to interrupt, but you're using tree level here? I mean, this is...
No. Here
this
no
is
tree
general,
level.
right?
This is general. This is general.
So, but in spite of that, you could not use this to obtain 2 to 2 away from this kinematic. Oh no, in n equals 2, you're not fixed to some q minus equal to 0 or something, right?
Yeah, but supersymmetry you need to still determine F4, right?
But you couldn't do it.
No.
The on-shell thing, we think we know away from everything.
Oh,
Yeah.
sorry, I
Yeah.
get mixed up.
Yes.
These are yeah. So the point is that all I need to determine F4, and I can choose the simplest thing. I choose this fiber phi cyber psi amplitude, okay, where color is contracted between fiber phi and cyber psi, and in the diagram there is only one diagram, this at the tree level, just fiber psi, which is like 4 pi by kappa. That's the answer for F4 with the wave function though for cyber psi. And that's the answer for F4, and that gives you all the possible scattering amplitude, including cyber psi, and cyber phi, fiber psi, okay, which are little more complicated to compute, but supersymmetry tells you how to compute. Okay, let me give you one thing, just one point more here.
So F4 directly gives you which amplitude?
F4 directly does not, yeah, F4, okay, no.
2 bosons, 2 fermions.
2 bosons, 2, no, sorry, I should be more careful. So q bar square, if I, yeah, so this becomes like ij angle bracket, which is like lambda alpha ij, and then it becomes theta I theta j, such that summation over I j greater than I.
So in particular, one of the amplitudes, would it give you two bosons directly?
No, so what it will give me is that F4 times lambda, let me call it, I am using this notation lambda, that will be related to, say for example,
2 bosons, 2?
to say I have to choose, like say, so in this notation, if you see that, suppose let me call my scattering amplitude 1, 2, 3, 4, then phi bar gets associated with a theta, so this is like theta 1. And psi bar no theta, so this becomes theta 4. So theta 1, theta 4 amplitude will be phi bar phi, psi bar psi with this color contraction. So all I need to do is that I need to F4, F4 lambda 1, lambda 4 will be same as this amplitude, which is like a lambda 3, lambda 4.
And so just say
Yeah.
how many bosons in the initial state, how many fermions?
2 boson, 2 fermions, say.
So 2 bosons to 2 fermions.
Yeah,
So
say
F
fermion.
form very directly gives you 2 bosons going to 2 fermions.
Yes.
In particle.
Yeah. And then I can find out from here all the others. Now there is a simple counting, but yeah. So at the level of one point I want to say that how this is actually at the level of
Sachin,
yeah.
3 minutes we'll have to leave the room. So whatever you have to say. Next.
Okay. Okay. So probably
Give 3 minutes summary, sorry.
yeah. So what I wanted to show was that at the level of 6-point function, although I pointed out that if I look at all the 6-point fermion and all the 6-point boson, they are not well behaved under BCFW, but there are other amplitude like
This is called BC?
no, not yet. So suppose I look at psi bar phi, phi bar psi, and phi bar phi. This amplitude, one of the example, it turns out that this amplitude is well behaved under BCFW reformation. Now where does it fit? The A6 will have say psi bar psi, all the 6 fermion amplitude plus this amplitude, say that will come with some particular theta structure. Point is that once you deform your amplitude momenta, BCFW deformation is momenta deformation, but you also want to keep on-cellness like p square is equal to 0 as well as momentum conservation to same. Also supersymmetry you have to keep it. It was noticed in one of the papers by earlier. That then also you have to deform your thetas, these thetas appropriately, okay? Because q bar is just lambda alpha theta, lambda I theta I. Now, because momenta deformation makes lambdas to deform, I also had to deform thetas to make it invariant. Okay. So if I deform that, it turns out that this particular amplitude, I choose this particular amplitude because under this deformation, this particular amplitude comes with a particular factors of theta which does not get deformed. And then it turns out because it's a supersymmetric amplitude, so this 6 fermion amplitude with the thetas, they will start behaving well. There is a little bit of story here, but that's the idea. Because if I get a supersymmetric amplitude, which is one component is really behaving well, actually we can show more components. Then because of supersymmetry, all the other component has to behave well. And then here I can show BCFW to work and write down in terms of product. Using that, I can write down the product for the other.
Okay, could you directly compute? You're saying that the end result of this is that you prove that tree level is exact.
No, not yet.
Sorry, you can compute tree level.
Yes.
No, you prove tree level is product of two corpora.
Yes. So this is at the level of, even at the level of supersymmetric amplitude, this is true.
Okay. Now for the particular amplitude that you looked at, could you just directly look at the Feynman graphs?
Yeah.
And
Yeah.
check that this is
Yeah. Exactly. That's how we started. Once that was confirmed, then one can use this, and so it predicts something for both fermion sector also, right? Fermion which was not getting product, now it's becoming like a product of two fermions. Now I can go over like for the case of fermionic theory, purely fermionic theory, that's true, or the n is equal to 1, that's true. So one thing nice though here is that suppose A6 does not get renormalized, then duality is manifest. That's why I think A6 won't get renormalized, because under duality A4 goes to A4, A4 goes to A4, and then A6 actually duality becomes manifest through this relation. So that's one of the motivation we thought that maybe it does not get really renormalized. But at this moment we think that even it gets renormalized, probably it also takes this structure. Not in the n is equal to, n is equal to 2, it really has to work out well. I don't know. But we are thinking that maybe in the case of non-supersymmetric situation where it really does not work, there it is possible to write in this product form.